few reminders I would like to remind you all of. Now, we've been doing this for close to 2 years now. You probably all know. Please mute your microphone, keep your camera off, and please turn your microphone and camera back on when you ask questions. We prefer to have questions toward the end. So if you have any questions, please keep them to the end, raise your hand and ask your questions, or post them in the chat. And towards the end of the presentation, Dr. A will take your questions. Feel free to use the chat box if you're having any technical issues, or if you can't hear Dr. A. And finally, please know this meeting will be recorded. We typically post our meetings on our YouTube channel right after the meeting for those who can't attend. So before I pass it to Dr. A, just want to say welcome to Dimitri. So for those who've been calling into our calls over the last year or two, you probably have seen me and Michelle. We were the two co-leads for this Seattle chapter. So starting this month, I'm stepping down, and Dimitri is going to take my place as the new co-lead with Michelle. So I'm going to give him a minute or two to introduce himself, and then you'll be seeing more of him in the future. So please join me and welcome Dimitri to this leadership position. Congratulations, Dimitri, and all the best. So I'll pass it to you to introduce yourself quickly, and then we'll pass it to Dr. Ray.
Thank you. Thank you very much, Ivan. And it's an honor to be replacing you, knowing the work that you put into the chapter. Everyone, my name is Dimitrios Athanasiou, and I'm from Greece originally. And I have a background in physics, undergrad background, but I switched over to environmental engineering because it was civil and environmental engineering because it was much more interesting. And I ended up doing a PhD on the topic as well. My interests around environmental engineering focus on contaminated sediments mainly, and also I'm looking at urban stormwater runoff and organic contaminants that are associated with it. So it's very relevant to Dr. Ray's presentation as well. I'm happy to be a part of it. As part, it's going to take some time for me to get used to the procedures and everything, but I would like to encourage everyone, if you have any suggestions, any type of suggestion regarding the chapter, always feel free to reach out to me and Michelle, and we would love to hear feedback on how to further improve the chapter. Yeah, thank you very much.
All right, I think with that, that's all we have. So, Doctor, if you want to take it over and start your slides.
Okay, sure. Let's see. Okay, everyone see that?
Yep.
Okay, great. So, yes, hi, thank you for inviting me to give a talk today about my research. So this is one aspect of my group's research. I'm an assistant professor at the University of Washington in the Civil and Environmental Engineering Department, and started there in 2019, so still pretty new. And we have research that is centered around development of materials to remove contaminants in water. So that's very in line with what I'll be talking about today. So to start, I wanted to, put into context this presentation, and that's really starting with the hydrologic cycle or the water cycle. So when we think about rainfall, the image I think that you conjure is one on the top right here, where you have rainfall over nice forested land, and the grass and the soil kind of soaks up all the water, and you can have replenishment of groundwater aquifers, stores, and this, again, natural flow of the water cycle. But, increasingly, a lot of the human population is living in urbanized areas, in densely populated areas. So instead of having this natural hydrologic cycle where you have natural infiltration of rainwater, you have instead rainwater, runoff or stormwater runoff onto roads that end up into water bodies. So you have, less volume of this kind of natural process and more urban runoff. And this is especially true in places like Seattle, as I mentioned, where we're a densely populated urban area. We have lots of impervious and engineered surfaces that, when the rainwater makes contact, it leads to high volumes of runoff on the streets. And this is, of course, not just an issue for Seattle, this is an issue worldwide. So this statistic by the United Nations projects that in 2050, 68% of the world's population is going to live in urban areas. So this is going to be a global phenomenon. And just kind of visually, this difference in rainfall over open forested land cover versus highly urban land cover can lead to significant changes in how water is managed and stored. So if you take an acre, for example, of forested land cover, here I stole this graphic from the King County wastewater treatment website, you can have about 800,000 gallons of water that is able to replenish, again, these groundwater aquifers, as opposed to 1 acre of engineered, surfaces and buildings and landscapes. You have the opposite. You have over 800,000 gallons of polluted runoff that ends up into the Puget Sound. So this kind of analysis exists in lots of, again, densely populated urban cities. And this alteration in how, stormwater is managed and stored, or, lack of, can lead to a lot of important implications. For example, over time, we'll have stress on the urban water supply as we get, again, less replenishment of groundwater aquifer stores. And we also, of course, have to deal with the increased pollution associated with rainfall, not making contact with open forested land, but instead making contact with these engineered surfaces. Some other statistics that I pulled from the King County website with respect to stormwater treatment and management is that approximately 1/3 of all pollution of water sources in Washington state comes from polluted stormwater runoff. And this has a lot of environmental and ecological impacts, including making a lot of the salmon and steelhead runs in the Puget Sound unhealthy because of contamination from urban runoff. So this is our current approach, I would argue, in most urban cities about how we manage our stormwater. It's viewed as a nuisance, and we need to get it off of the road to prevent scenarios like the image in the top left, where we have road closures due to urban street flooding. And we just need to get the stormwater off the street and then discharged onto a nearby body of water. But there are better ways to manage our urban stormwater. You've probably seen versions of these images around your neighborhood. So there are rain gardens that are, or bioswales that are installed to convey stormwater off of the street and then into these vegetated systems to promote local groundwater recharge. Same scenario here. These cutouts in parking lots that are there for aesthetic reasons, but could also help promote stormwater infiltration in cases where you would otherwise just have, pavement. Speaking of pavement, you could also have pervious pavement. That's pavement that is either porous or has these kind of open lattice networks that allow for grass to kind of pop out. And if you are fortunate enough to have larger land areas to do some stormwater harvesting and retention, you can build these retention ponds, as you see on the top image here. And, this is, of course, where we need to be going, but we could also go a step further in terms of how we manage our stormwater. So Seattle Public Utilities has incentivized, residences and commercial buildings to do some local rainwater harvesting. So their RainWise program, you might see signs around, again, your neighborhood. This is an image that I actually captured when I was out walking my dog. And you can harvest your rainwater on site to then use to irrigate your lawns at your homes, or on a larger scale, we can think about using stormwater or rainwater to irrigate our parks instead of using potable water that, you know, is drinking water quality. We could use stormwater here instead. And, you know, thinking about work that I was doing as a postdoc student at UC Berkeley, their water management and urban water supply is on a different level than ours because of the very likely scenario that they are under drought. So they were looking into ways to use stormwater as an emergency water store in case of extreme drought where more water supply is needed. The problem, of course, with realizing these more advanced approaches to managing stormwater is the presence of urban stormwater contaminants. So we'll talk a little bit more about this in a second, but you can have a variety of different sources of stormwater pollution. Some as blatant as, you know, dumping old chemicals and waste into storm drains. There's just, you know, that's due to just lack of public awareness about how our water systems are interconnected and how we should protect our storm drains. So this image on the right here. So where do these contaminants come from? There are unfortunately hundreds of thousands of different compounds that can exist in a typical, you know, urban stormwater. So for example, if you think about a suburb and then more kind of downtown urban area, there are many, many sources of contaminants that can be transported during rain or storm events to nearby bodies of water. So here are just a few examples. You can have actual litter and waste that gets run off into the street in case of heavy storm events. You can pick up trace metals from roofing and also from brake pads on cars, in addition to other kind of car-related pollutants like flame retardants and auto exhaust. In more suburban areas, you can have animal waste. Again, as a dog owner, I'm surprised to see how much dog poop is not picked up on, you know, my typical walks around the neighborhood. Pesticides and herbicides that are used to keep these lawns nicely manicured. Excess of, you know, those constituents, as well as excess fertilizer, can be washed from, you know, the streets and by the rainwater into nearby bodies of water. And this is important to consider because in most new cities, so cities built in the U.S. after the early 1900s, the storm drains are in separate piping networks from our sewage drains. So when you run your dishwasher, take a shower, clean your clothes, that piping network is usually separate from the storm drains. So of course, the water that we use daily for these activities gets sent to a wastewater treatment plant to be treated, but for stormwater, we don't have an equivalent for that, especially for, again, these newer cities. So all of these pollutants are going to end up in the Puget Sound or another receiving body of water. In fact, there has been recent studies by my colleague, Professor Ed Kaloje at the UW Tacoma campus and the UW Seattle campus that have linked pre-spawn coho salmon mortality to tire wear particles that get flushed into these urban creeks where the salmon are spawning. So I'm going to, let's see here. I'm going to drop in the chat the link to this YouTube video. Feel free to watch that after the talk. I don't know if I'll have time to actually play it during the presentation, but it's a nice video put together by the UW News team where they interview Professor Kaloje and Professor McIntyre, shown here, where they're actually in the field, you know, sampling from these urban streams where the coho salmon are actively dying. And it's because, again, of this compound they identified in tire rubber that was leaching into the stormwater and that was being conveyed into these urban streams. So now we're starting to see very severe ecological and environmental impacts associated with contamination of water bodies from pollutants in urban stormwater. So let's return to how we manage our stormwater and thinking more about these low impact developments that can be installed to help at least reduce street flooding, but hopefully can also provide some level of treatment for the number of contaminants present in these water bodies. So here's a figure from a review article that my group published last year, and we just sourced this data from an international stormwater management database. that is has data collections for a number of different what are called best management practices that can include grass swales or rain gardens, those retention ponds we saw earlier, and other similar systems. And they are tracking the contaminant levels into these systems and leaving these systems. And the top figure here shows the number of sites reporting data, and then we just show some contaminants, plot on the x-axis. And on the bottom here, we're plotting the removal efficiency for each of those stormwater systems and for each of the contaminants that we've selected. So here's some takeaways from this figure, and it's a lot to look at. The takeaways are that there are only few sites reporting any data. So if you think about your, again, walking around your neighborhood or just like, going about your errands and you see stormwater systems like these, there are often or not, no data is being collected from these systems. So whatever, comes in, we don't know what happens to those contaminants. This is because most sites aren't even reporting data. Of the data that is reported, there are, as you can see from this bottom figure, low to variable ranges of contaminant removal for certain classes of contaminants. And this is also not even considering that there are, again, hundreds of thousands of compounds present in urban stormwater, and there's only so much data being tracked for the data that is being tracked for how many contaminants are present and how many are being removed. So there's, of course, non-targeted approaches where instead of saying, I'm going to look for zinc or lead or, this particular herbicide or insecticide, there are, again, hundreds of thousands of contaminants that we're not even tracking. So this is concerning, and we need to think about better ways to improve contaminant removal in these stormwater systems. So if you think about, again, this example of a stormwater system, say a bioretention pond, where when you have rainfall and an influx of contaminants into these systems that are, transported through this bioretention pond and eventually out to a storm drain, you can rely on the use of conventional materials that are usually found in these systems, like sand, gravel, compost, the microbes inside the soil that can help facilitate biodegradation of some compounds. But we need more, at least that's what the data suggests. So what our group is doing is we're developing low-cost engineered materials that are also environmentally benign that could be amended in these systems to improve contaminant removal. So I'll give you an example of one material that we are investigating, and that is an adsorbent made from agricultural food waste, and it's called biochar. The bio in biochar comes from a biomass food stock or feed source, and you can use a number of different options. Typically, it's some compostable agricultural food waste product that you have excess amount of, and you burn that at high temperature to generate a charcoal-like material, hence biochar. And for our biochar material, we decided to use spent coffee grounds or used coffee grounds. So our particular coffee grounds for the data that I'll present here in a second are actually sourced from our dining services on campus. They use about 90% of it is Starbucks coffee. I want to say it's pipe roast coffee grounds. And this is a great option for us because carbon happens to be a very carbon-rich material, which is important for the ability of other biochars and activated carbonaceous materials to remove contaminants in water. And also, we have an overabundance, particularly in the Seattle area, of used coffee grounds. In fact, Starbucks has this program that you might have seen at your local Starbucks called Grounds for Your Garden, where they literally give away bags of used coffee grounds to customers to use to fertilize their lawn. So we have plenty of feedstock material, and it also happens to be separated from other compostable food waste as well. And if you kind of zoom in and take an image of this biochar, this is an image that my PhD student captured, you can see that depending on the feedstock, you can have large kind of networks of pores present in the biochar, and contaminants like heavy metals and organic compounds can diffuse into the pores to be effectively removed. So biochars have been investigated for a number of different water treatment applications, and it has some clear environmental benefit because the alternative is to use activated charcoal, which is sourced from charcoal, which is, of course, not an environmentally sustainable material. So if we can use some other, source material besides charcoal that can also work as well to remove contaminants in water, and that's a huge benefit in terms of how sustainable this operation is. So I'm going to present some data that we've collected about the biochar that we generated in labs. That's a picture of what it looks like for different contaminants that are found in stormwater. So first, what we did was we wanted to take our source material, the used coffee grounds, and then burn the used coffee grounds at different temperatures to then investigate how well those different temperatures remove or help to remove contaminants in the finalized product. So here we investigated temperatures of 400, 600, and 800 degrees Celsius. And then here's the surface area corresponding to those temperatures. So you can see these are pretty low surface area materials, and we were a little bit concerned about that. And we did some preliminary testing with the different materials shown here with a representative urban stormwater contaminant, which is PFOS. Here's the structure here. I'm sure you all are familiar or have heard of these PFAS compounds that are unfortunately very, environmentally widespread and dispersed, and also unfortunately acutely toxic. And PFOS is one of the over 5,000 different types of PFAS, and it happens to be one of the most commonly detected. So that was why we started with this particular contaminant to investigate how well our material works for water treatment and specifically stormwater treatment. Okay, so first we examined, again, the different pyrolysis temperatures and the ratios of how much biochar is present in our reaction systems versus how much PFOS is present. So we did a 24-hour batch adsorption test where on the y-axis we're plotting the measured equilibrium PFOS concentration in solution. On the x-axis we're plotting the dose of biochar in the system. So here it's from highest to lowest dose, so 200 milligram of biochar per liter of reaction solution that contains the PFOS. Excuse me. And here the different color bars represent the different pyrolysis temperatures. So we started with 50 microgram per liter PFOS in solution, and as you can see here, we're getting about very low removal. So we're measuring around 50 microgram per liter PFOS in solution. So we have poor PFOS removal. There's no significant difference that we could discern based on the pyrolysis temperature, and we hypothesized because we have low surface area, as you can see in this table here. So what we did next was we, took advantage of knowledge around pyrolysis of other carbon-rich materials, in particular, the activated charcoal that's used for water and wastewater treatment. So the activation step can be done in a bunch of different ways, but during activation, what you're doing is you are creating more surface area within the material by doing an additional pyrolysis step in the presence of some chemical activating agent that allows for this increased surface area, which we hoped would help improve PFOS removal. So what we did was, again, we plotted percent PFOS removal this time on the y-axis, still 50 microgram per liter, still a 24-hour batch absorption test. And here we tested two different chemical activating agents that were added in during the second pyrolysis step. So the dark green kind of squares here indicate where we added in a certain mass of sodium hydroxide versus the lighter green circles where we added potassium hydroxide. These are both caustic materials, so we wanted to, achieve this activation and increase in surface area without having to rely on, too much of this caustic material, because again, we want to make sure this process is going to be environmentally benign and not result in a lot of, extra contamination. So on the the x-axis here, we're plotting the mass ratio of the either sodium hydroxide or potassium hydroxide that we've added to grams of the spent coffee ground biochar pyrolyzed at 400 degrees Celsius, this SCG 400. So we can see that typically the higher mass dose of the activating agent that you add, the greater the PFOS removal. We decided to consider this 1 weight percent, so 1 gram of potassium hydroxide to 1 gram of the biochar material, to proceed with further testing because, again, we wanted to minimize both energy input and chemical input. So we chose 400 degrees Celsius because that was the lowest pyrolysis temperature that most carbonaceous or biochar materials are prepared using, that low temperature. And then also we wanted to keep the addition of chemical activating agents low. So we didn't want to, add, like 10, 15 grams of either sodium hydroxide or potassium hydroxide. We wanted to keep that low to, reduce excess waste and potential toxicity with how caustic these materials are. So when we did that, we did a second test with a different batch of coffee grounds to see, how reproducible is both the initial pyrolysis and this activating step. But we can see that even with a different batch of coffee grounds, that we have comparable PFOS removal. So that's good news. And what's even better news is, again, the addition of that potassium hydroxide here, we're calling this SCG-KOH for potassium hydroxide, did significantly increase the surface area of our biochar material compared to this very low surface area of the SCG 400 that we started with. So that's great news. Okay, so that was some initial characterization of the activated biochar material that we've been developing in my group. And what I wanted to do, or what we wanted to do next, was to start answering questions about how well this material could work to remove contaminants in stormwater. So here on the left here, I'm showing lab scale columns that we built. And what's missing in this picture is this large tank at the bottom where we have tubing coming from that is injected up and then out the top of the column. And we have spiked this synthetic stormwater mixture that we created in the lab with different contaminants to mimic stormwater that would enter into a rain garden, for example. And then from left to right here, we have triplicate columns of either sand only, and then sand dosed with different weight percentages of the activated biochar. So either a 0.5 weight percent amendment of the biochar or a 3 weight percent biochar amendment. And the idea here is that in a typical rain garden, sand is very commonly used. And if you add too much biochar, you could have a lot of adverse impacts, such as like clogging, for example. That's been reported in some systems investigating applications of biochar during infiltration processes. So we just wanted to dose the sand with a bit of the biochar to increase contaminant removal, but also maintaining certain hydrologic flow patterns in a typical rain garden scenario. Okay, so those are the columns that we built, and then the contaminants that we investigated have a range of hydrophobicities. That's the log KOW values reported here. And they also range from, different representative trace organic compounds in stormwater. So we have some herbicides, insecticides. We have a wastewater pollution indicator. Caffeine is very commonly found in both wastewater and surface water. And again, insecticides and disinfectants as well. Okay, so again, this is all in a synthetic stormwater matrix that contains some organic carbon to really just mimic how well the biochar can remove compounds in a representative stormwater matrix. So here are the figures I'll show in a second, have the different compounds that we've spiked into this synthetic matrix. And here we're plotting the performance of the columns in terms of pore volume on the x-axis. So a pore volume is, one pore volume is the amount of water that could be contained in our columns in their packed configuration. So packed, again, with either sand or biochar. So the more pore volumes that are treated, the more volume of water has passed through your column. And then on the y-axis, we're plotting normalized contaminant removal. So measured concentration over initial concentration present in the stormwater matrix. So low values means very high removal. Values of 1 means that whatever contaminant you put in is coming out of the column, so no treatment. So not surprising here, when we have sand only, there's this rapid breakthrough. So the contaminant that enters the column is pretty, just exits the column rather quickly. And we're not surprised there. We know that sand is not great in terms of removing trace organic compounds. When we slowly start to increase the amount of biochar in the system, we see that for some compounds like caffeine that happens to be pretty hydrophilic, we have more or less immediate breakthrough compared to some treatment of the other representative urban stormwater contaminants. And then when we increase the amount of biochar in our columns further to 3%, you can see that we're able to treat, many, many pore volumes of water, of stormwater in this case, and we're still, these columns are still operating, and we are still removing contaminants, even with just 3% biochar, which happens to correspond to about 4 grams of biochar in a column packed with 200 grams of sand. So if you could extrapolate that further, you can hypothesize that, to a certain extent, again, without impacting the physical flow of water through these systems, you could add a lot more biochar and get a lot longer, removal of these contaminants in water. So the data that I'm showing here is for, of course, select trace organic compounds, and we're going to do some further probing into abilities of the biochar to remove other types of contaminants like trace heavy metals. So we're really, excited about the preliminary data that we've collected so far in mimicking infiltration stormwater systems like rain gardens, and especially how it compares to materials that are already used in water and wastewater treatment, such as commercially available activated carbon or charcoal. So here are some kind of comparisons between our material and activated carbon. Of course, using coffee grounds has many benefits, including the ones that demonstrated in the data I presented, but also because this material or this feedstock is going to be composted already. So we are taking a food waste product and we are upcycling it into an adsorbent that could be removed or used to remove contaminants in stormwater. It's it's a new technology, but it's based on an existing material. So hopefully, once we demonstrate further its capabilities, we could think about future applications where the coffee ground biochar could replace activated carbon in water treatment systems, such as in stormwater filtration. And what we're going to investigate in the future is how to dispose of the coffee ground biochar once it's done removing contaminants. So with activated charcoal, what you do is you would just kind of pyrolyze or re-incinerate the material to hopefully burn off the contaminants that are adsorbed and then recover the adsorbent. Here we could think about other alternatives for disposal that are less energy intensive, like composting, which is what you would do with used coffee grounds anyway. So these are things that we're going to investigate in the future. And again, we have some hope for this material because we did a test comparing our used coffee ground biochar to a commercially available activated carbon that's used in water and wastewater treatment. And under certain conditions, we have, equal removal of, compounds like PFAS that are, again, really toxic and pervasive in the environment. So these types of comparisons we'll also be making in the future. Speaking more about, PFAS, I'll have like 2 more slides here, I promise, and leave some time for questions. In thinking about applications like stormwater treatment, we were excited about using biochar sourced from a more environmentally sustainable material because the biochar, as our data suggests, and as other studies investigating different types of biochar have suggested, is that it's able to remove a wide variety of contaminants in water. So not just organic contaminants, but also inorganic contaminants like heavy metals, also nutrients, even pathogen removal can be facilitated by biochar, which is great because in stormwater, unfortunately, we have mixes of different types of contaminants present. For certain contaminants like PFOS or PFAS, we are thinking a bit about specificity here, because if you think about, say, stormwater, for example, that again has mixtures of different types of contaminants, including PFAS, we know that PFAS are more toxic and more environmentally persistent compared to other compounds and contaminants. So we might want something that is going to actually target the PFAS in water, as opposed to some just typical non-selective adsorption like you would get with an activated carbon or with the biochar. So what we're doing is we're taking advantage of a technology called molecularly imprinted polymers, or MIPS. And here's a schematic showing how you prepare this type of polymer. So you can start with some functional monomers or just reagents to preparing the polymer. And then you can add in a compound of interest, say, for example, PFOS or another PFAS compound. And then you polymerize the material. So you kind of blend and mix everything together to form a polymer that's represented by this structure here. And then you can do an extraction step at the end where you remove the compound of interest that you started with, and then you generate this kind of Pac-Man-like shape here. And this is the final molecularly imprinted polymer configuration. So the idea here is that you get a lock and key type removal mechanism where this particular polymer should only remove the compound that you started with. So that's how you impart the selectivity and the more targeted removal. So what we're doing is, I should back up. So this has been done for the last, like 80 years or so, and it's been used for applications like detecting certain drugs within mixtures of drugs and solution. It has also been used to remove contaminants in water. So if you want to target compounds like PFAS or other organic compounds or inorganic compounds, there's versions of this material that have been, very well studied in the literature. The problem is when you do this type of polymerization, you end up with a very fine powder. So that's not something we want in, let's say, a stormwater infiltration system, because that'll just get washed through and then you might not even get removal of the contaminant that you're hoping to remove in that case. So in order to achieve the selective removal while, doing it in a way that makes the final product more, robust and stable to actually be placed in a stormwater infiltration system, what we're doing is we are taking the SCG-KOH, that's our activated youth coffee ground biochar, and we are doing this polymerization in the presence of the biochar. So we've modified the biochar surface to then prepare it for this subsequent polymerization. So here, for example, we can use PFOS as a template compound of interest during polymerization. We add in all of the other polymerization reagents, and then we can make a molecularly imprinted polymer that is coated on the surface of our very granular biochar material. So that way you can, again, have the selectivity for PFAS on a substrate that is more robust, more stable in these stormwater infiltration systems. Okay, so some next steps in future directions of this work, we again want to do some more testing in the lab in terms of controlled conditions of what types of contaminants can be removed, what range of contaminants in terms of concentrations of removal. We can do some calculations and predictions for how long the biochar would last under these conditions in a real stormwater infiltration system. We can also answer questions of, what happens in the likely scenario where you have intermittent flow, where it rains, for a while and then it doesn't rain for another 3 days. Like how how stable is a biochar material or the modified biochar material under these conditions. So those types of analyses we can do in the lab under controlled conditions with the hopes of piloting the technology in the future to do some real stormwater treatment. So to do that, we've been talking with a lot of different agencies and organizations. The Tacoma Center for Urban Waters does a lot of piloting of new water treatment technologies. The Washington State Department of Ecology actually has a certification program for new stormwater treatment technology, so we could get this material certified. That would also help facilitate translation and dissemination. And water and wastewater treatment divisions like King County, as well as Orange County and in California, are interested in piloting new treatment technologies. And again, with the activated biochar being similar to an activated charcoal material, we think it would be very easy to do this kind of swap to do some piloting in a small scale water treatment facility. And then due to the sustainable nature of how this material is made and how it could potentially be disposed of, we have gotten interest from these nonprofit organizations like the People for Progress in India that are looking for low-cost water treatment technologies to remove contaminants in different water sources. Oops, okay. I think actually that's the end of my talk. So I will stop there. If there are any questions, I can take those now.
Excellent. Thank you very much for the presentation, Dr. Ray. Before we have a number of questions on the typed in the chat, but before we get to those, I was curious if somebody would like to ask, turn on your video and ask a question directly to Dr. Ray.
I can also just start answering the questions in the chat if there's no questions over Teams. Let's see. So the first question by Brian, adsorption only, or is there subsequent biodegradation occurring in the columns? Yeah, that's a great question. So right now we are right now we are investigating adsorptive-based removal, but of course we could, push these systems to start promoting biodegradation of compounds within the column. So in order to do that, we need to do a kind of mirrored study. So what I forgot to mention with the synthetic stormwater matrix that we created in the lab, we added sodium azide to kill off any bacteria that might be forming over time, especially because working with biochars in the past, I hypothesized that it was going to take a very long time, like on the order of months before we can, conclude the study. So the likelihood that biofilm formation would occur is very high, which is why we added the sodium azide. So we could do an additional study where we actually let the system run for a while to promote that biofilm formation and then compare and contrast how the contaminant removal is, I suspect, improved by the development of a biofilm within the material. So yeah, that's a great question.
Thank you.
Yeah. Scott's question, did you look at nitrate and phosphorus concentration in the effluent? So do I have that matrix here? Let me see, I had a whole bit about PFAS we didn't really talk about. Okay, nope, it's not in this talk. That's unfortunate. So I usually have a slide about the synthetic stormwater matrix. So we did add some nitrate and phosphate into our synthetic stormwater matrix, in addition to like calcium, magnesium, chloride, other representative kind of inorganic species that you would typically find in stormwater. And we were primarily concerned, at least at this point, with the removal of trace organic compounds in the system. We do have, of course, all the samples that we collected, so we could do some additional analysis in terms of the nitrates and phosphates that were removed in the system as well. The levels of nitrate and phosphate that we added into our synthetic stormwater matrix were what you call background concentrations. I'm more curious, again, in a separate study about scenarios where you have stormwater runoff from, say, an agricultural land application where the levels of nitrates and phosphates would be significantly higher than what we've added into our system. So that'd be interesting to study in the future for, again, a separate study than what we're doing now. That is one benefit of other biochar studies that have investigated applications for stormwater treatment is they do report removal of nitrates and phosphates with biochar. So that's something we can also investigate, and also potential, I guess, competition with other contaminants that are present in stormwater.
Yeah, could I just follow up on that briefly?
Sure.
So you're probably aware of all the work that demonstrates actual leaching of, so when you have compost amended biossoils, that we have leaching of nitrate and phosphorus, and that's, when you're looking at groundwater contamination, nitrate is a particular concern, as well as, what ends up in surface water. So anyway, I'm just, that would be one. I'm hoping that the burning of the material actually reduces that leaching of nutrients from the material.
Yeah, that's a great point. So we should look into, in addition to leaching of nitrate and phosphate, we should look at also just leaching of dissolved organic carbon from the biochar. That could also have some impact downstream. And then what else is it going to add? So in terms of the pyrolysis and what else could come off of the biochar during application, what we did make sure to test is that we don't leach caffeine into the stormwater that we're trying to treat. I think that's a question that comes up a lot, is like you're using coffee grounds, so there must be caffeine around. So the other nice thing about the activation step that we did, where we added in the potassium hydroxide, which increased the surface area, but that also helped release a lot of residual caffeine that was trapped inside of the biochars that we burned at much lower temperatures and without the chemical activations. That was another benefit of that step. But yes, we should absolutely look into not only the ability of the biochar to remove nitrate and phosphate in water sources, but any potential addition of those species into the water as well.
Well, it sounds like exciting work you're doing.
Great, thank you. Okay, so Brian also asked about the ability to scale up this system. That's something we'd absolutely love to do. So this particular material is now patented. That was pretty recent that happened, and we had received funds from University of Washington CoMotion Innovation Hub. They help kind of support startups that spin out of research at the University of Washington. I honestly have not thought that far ahead yet. It's, trying to support a startup based on this material is very exciting, but honestly outside of my bandwidth right now. So I'd like to, push, think about that in the future. But one obstacle that we have is the amount of biochar that we're able to make in the lab currently. So there are some manufacturers of biochar throughout the Washington area that have, for example, like larger ovens that could help us produce more of the biochar at scale that would be needed for, implementation in piloted stormwater infiltration systems or wastewater treatment infrastructure. So that's where we're going. We're not quite there yet.
I do have a bit of a follow-up question on this, Dr. Ray. If you go a few slides up, I remember a slide where you were talking about pore volumes, and you were talking, in the order exactly this one.
Yeah.
So let's say if we have 1 cubic meter of this material, what is the percentage of the pore space in that material? How many gallons would it be?
Okay, so one pore volume for, it depends on how much biochar is present in the column as opposed to just sand. So for the 3 weight percent column, one pore volume at the flow rate that we've selected, which is 1 millimeter per minute, which is comparable to stormwater infiltration rates that you would get in a real rain garden. The pore volume is about, I want to say 80 minutes. So you can just do an analysis with 1 pore volumes about 80 minutes at a 1 milliliter per minute flow rate. So you can convert that into volumes of water treated. For the 3 weight percent biochar columns, we are at, I think, about 200 liters or so, 250 liters of water treated. And again, this is still ongoing. So these are part of the calculations that we're doing. So we can say, for example, model a typical rain garden system where you'd have a certain area and depth of a layer of biochar sand mixture that you're adding, and then do some calculations, at least based on the conditions in this study, of how long the biochar's lifetime would be before you would need to replace the material. I'll say that, at least based on rough calculations, that we're getting, theoretically decades of performance with a very low amount of biochar. So we, like I said, have so many different research directions and questions associated with this material and how well it can perform and how we get to that next step of implementation. So some analysis includes more information about its hydraulic conductivity, which is important to understand, because if, as we suspect with this material, it is not able to clog, say, your column or an infiltration system, which is a big concern with a lot of carbonaceous materials, that it, in addition to absorbing contaminants, it can also absorb water. So we don't want that in an infiltration system, because it then would clog the rain garden in that case. So if my hypothesis is, true, that the coffee ground biochar does not absorb water that well, at least based on its the pore structure and kind of other physical properties that we've kind of tested with the material, you could add a lot more than just 3 weight percent biochar into a rain garden. In that case, you can get even longer lifetimes. So these types of questions we're going to look into in the future. Many questions with this material. So yeah, let's see. Yeah, so with the Kathy's question, we are, in addition to, kind of connected to Brian's question about scaling up, that is actually, in terms of stormwater management, there's a lot of folks looking into, ways to either install or design rain gardens, less so for addition of media or reactive materials that could help with contaminant removal. So we don't have a wealth of industries and companies to chat with in terms of production of material in case our biochar to add in these stormwater systems. But in terms of the, King County wastewater treatment division, who also handles the stormwater management, we are chatting with them to see if they're interested in our material so that we can, again, get these next steps of how to scale up.
I wanted to pipe in there. I'm Steve Nelson, the next comment up
Okay.
here. And I just wanted to point out for the group that right now EPA, this is on the pyrolysis, on the production side, EPA has issued an advance notice of proposed rulemaking related to pyrolysis and gasification. The comment period closes, I think, December 23rd. One of the options that is explicitly on the table would be to regulate the pyrolysis production process that you described here as solid waste incineration, which would put the process under a very restrictive set of permitting, air emissions permitting conditions. I'm also have been involved with the air emissions permitting for the biochar facility that's under construction in the city of Edmonds right now at the wastewater treatment plant.
Oh, great. Yeah, thanks for that information. That's really helpful. That'll be, thinking about disposal mechanisms for the youth activated biochar that we're investigating. If we can, find ways to, get the composting configured so that we can just get degradation of the compounds, absorbed into the biochar as it's composting, I think that would be a significant gain for application of our material as opposed to regular activated carbons that are just, again, re-incinerated or repyrolyzed to degrade contaminants and then reactivate the material. Okay, I think I have time for one. I have a meeting at 1, sorry. So I have time for one more question.
We're almost at the top of the hour.
Yeah. So there's a lot of comments about the 6 ppd cleanone that was the tire rubber leachate compound that was identified to result in that urban stormwater coho salmon mortality. So we are looking into the ability of our activated biochars to remove those compounds, and then the next step again in thinking about PFAS selectivity using the activated biochar that's modified with the polymer material. We're also, of course, trying to extend that to the 6 ppd product so that we can get selective removal of that compound, which we know is linked to that coho salmon acute toxicity. So yes, absolutely. That's and I've been talking with Professor Kolodziej for a while now about plans for this test.
Excellent. Dr. Ray, thank you very much for your presentation, and thank you everybody for being part of this talk. And yeah, we're not going to have a meeting next month due to the vacations, so we're going to reconvene January. Is that right, Ayman?
Yep, that's the plan. We're gonna have we're hoping for another year of really great speakers. So we thank you, Dr. Ray, for concluding a great year. We had plenty of good speakers from academia, from industry, from consultant firms, and from nonprofits and tribes as well. So we're hoping for another lineup of speakers. But again, we still have some slots available for next year. So if you have a project or something you would like to talk about to our group, please contact Dimitri or Michelle. And that's all we have. So I think we're a minute past the hour, so we'll let you go. And have a great holidays, everyone.
Great. Thanks so much for letting me come chat. It was fun.
Yeah, absolutely.
Thanks. Bye.
All right.
Thank you.
Bye.
Hey, by chance, does anybody have the link to that EPA commenting period? It'd be great if we could provide public comments.
Absolutely. That would be great.
I can provide the link if you tell me who to send it to.
Thank
Want
you
to put
very
it in the chat?
Hey, Brian? Okay, I'll